Welcome to the lecture series on numerical methods, a finite difference approach. And last class we have discussed about the various solution methods for ordinary differential equations, and in this lecture we will start about partial differential equations. And in this partial differential equation solution approach, first we will just go for this classification of partial differential equations. So whether it is like parabolic, elliptic or hyperbolic, and based on that we can just proceed for the solution methods. So especially if you will just go for the contents here, first we will just go for this introduction of partial differential equations, then this classification of partial differential equations, then how we can just represent this partial differential equations in a standard form, and then we will just describe the boundary conditions through which we can just obtain the solutions of the partial differential equations. So partial differential equations are equations that involves functions and its partial derivatives with respect to two or more independent variables. This means that in ordinary form, especially if you will just see that we used to write dy by dx. This means that y is the dependent variable and x is the independent variable here. But if you will just go for like differential equations with more than one independent variables, then it is called partial differential equations. So any partial differential equation, it can be represented as a function like u is a function like x1, x2 up to xn, then its partial differential form can be written as either as del u by del x1, del u by del x2 up to del u by del xn, or del square u by del x1 del x2 up to del square u by del x1 del xn, or so many forms in partial sense we can just express. So that is why a partial differential equation for the function u, which is a function of like variables x1, x2 up to xn, is an equation of the form that is f of x1, x2 up to xn, del u by del x1, del u by del x2 up to del u by del xn. Then this is especially your first order partial derivatives. Then if you just go for second order partial derivatives, it can be written in the form of like del square u by del x1 del x2 up to del square u by del xn del x1 del xn. So afterwards similarly we can just express this partial differential terms up to nth order. So this partial differential equation, if you will just see, it is occurring in all classes of engineering problems, specifically when this wave propagation problem if you will just see. So one dimensional wave propagation equation, it can be represented in the form of like del u by del t equals to c del square u by del x square. That is nothing but a partial differential equation. Then this fluid flow equations like continuity, governing equations like momentum equations, energy equations. So all these equations involving the partial differential equations of first order, or it can be of more than one order. So then like vibration problems, if you will just go for this mechanical systems, so there also we can just find this partial differential equations which expressed in different forms. So then this mechanics of solids, that is solid mechanics problems, if you will just discuss like tensor fields or like stress fields, then usually it can be represented either in the two dimensional space or in three dimensional space, which can be represented as a tau of xx, tau of xy, tau of yz. So all these forms can be represented in the partial differential sense. Then heat flow and distribution, that is especially if you will just go for like one dimensional heat transfer equation or two dimensional heat transfer equation, then we can just find different class of partial differential equation. Then diffusion of chemicals in air or water, especially if you will just using this cigarette smokes, you can just find this diffusion model there. Especially if you will just write that is the equation in the form of del square u by del x square plus del square u by del y square, then we can just find the diffusion equation terms there. Then if you will just discuss here electric field and potentials also like Maxwell's equation or like any class of like electric field equations, that also like expressed as in the form of partial differential equations. So based on this, if you will now go for this like classification of partial differential equations, so first we want to express this partial differential terms in a generalized form. So, many physical problems can be represented by a second order partial differential equations. If you will just see in the textbooks or in like natural phenomena problems, whatever these researchers are using, especially that is represented in the form of second order differential equations in partial sense. If we can just express this generalized form as a del square u by del x square, we can just express this one as in the form of like del square u by del x del y or del square u by del y square. So, plus E means it can be involved either this first order partial differential terms or all of this like dependent variable terms or independent variable terms. So, that is why we have just kept E as a source term here, and all other terms are as the second order partial differential terms here. So, that is why I have just written it up here, that is if the partial differential equation in second order form can be expressed as a del square u by del x square plus b del square u by del x del y plus c del square u by del y square plus E equals to 0, where a, b, c and E may be the functions of either x, y, u, ux and uy. So, then when we will just go for this classification of partial differential equation, if you will just consider this equation which is represented as 3.2 here at any certain point, suppose x0, y0, this depends on the sign of the discriminant defined as delta of x0, y0 equals to determinant of this coefficients. If you will just see this diagonal coefficient b as written here, and especially this is the coefficients that is just represented as a 2a here and 2c here. Especially if we can just discuss about quadratic equations. So, usually this coefficients that is written in the form of x square plus 2bx plus c equals to 0. So, there itself b always involves this coefficient 2. So, that is why if in a generalized sense, if we can just express the partial differential equation as like 2a, 2b, 2c here. So, then we can just see that this coefficient b can be taken out as in that form, but remaining coefficient for like u with respect to x and u with respect to y, it is like 2a and 2c here. So, that is why this coefficients for like del square u by del x square is written as a 2a here, and for del square u by del y square it is just written as a 2c here. But the coefficient, since in the earlier or in the beginning of the sequence or these equations, especially it is just written as a coefficient of 2b. So, that is why there itself also, so b is taken as the coefficient. That is why we can just write this determinant as b, 2a, 2c and b, and its determinant can be expressed in the form of b square minus 4ac here. So, when we have just defined these coefficients in a determinant form here, so we can just define or classify this partial differential equation as, if suppose this determinant is greater than 0, the equation is hyperbolic, and if this determinant equals to 0, this equation is parabolic here, and if this is less than 0, then this equation is elliptic. Especially in mathematical sense, if you will just write all these coefficients as b square minus 4ac, if it is a 0 here, then this system is said to be parabolic, and if b square minus 4ac is less than 0, then the system is said to be, it is in elliptic form, and if it is greater than 0, then we are just saying it is in hyperbolic form. So, that is why a partial differential equation may be of one type at a specific point and of another type at some other points also. This above classification can be represented if you will just consider like another example. Suppose consider a partial differential equation like del square u by del x square plus del square u by del y square equals to 0. So, if you will just compare this equation with our earlier equation term, then we can just find these coefficients as like, if you will just see here, del square u by del x square plus del square u by del y square, this equals to suppose 0 here. So, earlier our equation we have just defined that as in the form of a del square u by del x square plus b del square u by del x del y plus c del square u by del y square plus E equals to 0. If you will just compare these coefficients here, del square U by del x square coefficient is A here, del square U by del y square coefficient is C here, but this B coefficient, especially this is just taking the 0 value here. So that's why we can just represent this one as B as 0 here, A as like 1 here, C as 1 here. So that's why this total value, that is B square minus 4AC, that is nothing but we can just write 0 minus 4AC, since A equals to 1 here and C equals to 1 here. So that's why this total value is coming as minus 4 here, and especially minus 4 is less than 0, then this condition, especially if you just see the previous slide here, that means that if B square minus 4AC is less than 0, then the system is elliptic in nature. So that's why therefore the equation is an elliptic equation here. So for the example, if you will just consider like a one dimensional heat equation, then this partial differential equation form is del u by del t equals to del square u by del x square. So people used to write this one in the form of like del u by del t equals to c del square u by del x square, where c is the like specific heat constant. And here if you will just see the coefficients, so especially these coefficients, this can be written as here del square u by del x square coefficient is 1 here, and like remaining coefficient, that is c equals to 0 here and b equals to 0 here. So that's why b square minus 4ac, if you will just see, this is just taking the 0 value. So that's why this is an parabolic type equation, and 0 condition means we can just say that the system is parabolic in nature whenever b square minus 4ac equals to 0. So then if you will just go for a partial differential equation in a generalized form, suppose generalized form means in the previous slide I have just told that whenever we will have certain domains in certain ranges, we can just say that the system is like parabolic. In certain domains we can just say that the system is elliptic in nature, or certain domains where this system is like hyperbolic in nature. So to classify this one, we have considered this example as like this partial differential as x plus 1 into del square u by del x square plus 2 into x plus y plus 1 del square u by del x del y plus 2 into y plus 1 del square u by del y square, this equals to 0 here. So if you will just see this equation here, then you can just find this coefficient of b as 2 into x plus y plus 1 here, and the c coefficient that is as 2 into y plus 1 here, and a coefficient that is nothing but x plus 1 here. So you can just write a equals to this one, b equals to this one, and c equals to this one here. So that's why b square minus 4ac, if you will just consider here, that is nothing but 4 into x square plus y square minus 1 here. So there itself we can just justify that 3 conditions can be taken to define the domain where the system is like parabolic, where the system is elliptic, where the system is hyperbolic here. So if you will just consider the system that whenever suppose x square plus y square value, if it is less than 1, then the whole system will take a like a negative value here. That is the given equation is elliptic inside the unit circle, that is x square plus y square less than 1, and parabolic on the circle, that is x square plus y square equals to 0, and hyperbolic outside the circle for x square plus y square greater than 1 here. So from these equations we can just justify that within certain domain we can just say that wherever this the system can just represent a parabolic nature or a hyperbolic nature or a like a elliptic nature. So if you will just define the domain like x square plus y square, this is just equals to 1 here, then we can just say that how it is just behaving inside the system here. Suppose if we are just considering inside this circle only or above the circle only, then we are just saying it is parabolic in nature, but outside this range it is just showing a different nature, and inside this one it is just showing a different nature here. So then in a generalized form, if you will just consider a second order partial differential equation in 3 independent variables, suppose, since in the like two variable sense or in a like second order partial differential equation sense, we are just saying that we will have these coefficients like a, b and c. So, based on that we are just classifying that whether this b square minus 4ac is greater than 0 or it is less than 0 or equals to 0. But if it is more than like two variables, then we will have like several coefficients in that scale. So, if we will just go for a partial differential equation in three independent variables, suppose that is suppose x, y and z, and if we can just write this system as like axs and del square u by del x square plus ayy del square u by del y square plus azz del square u by del z square plus 2axy del square u by del x del y plus 2ayz del square u by del y del z plus 2azx del square u by del z del x plus bx del u by del x plus by del u by del y plus bz del u by del z plus cu equals to 0. Especially if we want to write this one like in a compact form, we can just signify these three terms or this last added terms as e terms here. Since remaining terms, if you will just see axx, ayy, azz, axy, ayz and azx, which just consists of all these variables which are of second order in partial differential sense. So, if we can just go for this classification of this partial differential equation here. So, then we can just define these coefficients in a matrix form as A equals to like all these x derivative terms in the first row here, that is axx, axy, axz here. For the second one, if you will just go, we can just define that one in a opposite sense as a of yx, a of yy, a of yz here. So, then third one we can just write a of zx, a of zy, a of zz here. This means that each of these independent derivatives, if you will just combine like 1, 2, 3 here, then we can just write this one as like 2, 3 here. So, especially the first diagonal entry we can just write 1, 1, then this is 2, 2, this is like 3, 3 here, and all other differentiations are with respect to like second one it is differentiated with respect to y here, then first one it is differentiated with respect to x here, third one it is just differentiated with respect to z here. Then if you will just determine these eigenvalues of matrix A are the roots of this characteristic equation of matrix A here, that is nothing but modulus of A minus lambda I equals to 0 here. And with the help of these eigenvalues, we can just classify this partial differential equation whether it is parabolic in nature, hyperbolic in nature or elliptic in nature. So, the first condition is that if all eigenvalues are non-zero and have same sign except precisely one of them, then equation is hyperbolic in type. This means that suppose we will have these roots like 2, 2, minus 3. Then 2 consecutive it is just repeated and 1 is different, and if we are just getting the roots are like that, then we can just say that it is hyperbolic type. So, that is why this condition is written that the eigenvalues are non-zero and have same sign except precisely one of them. So, that is why we can just write this one as suppose 2, 2 minus 3. Then we can just say that this partial differential equation is like hyperbolic in nature. Then we know that if this determinant equals to 0, at least one of the eigenvalues is 0, then in that sense we can just say that the system is parabolic in nature. But if all the eigenvalues are non-zero and have same sign, then the equation is elliptic type. So, especially if we can just write this one as like 3, 3, 3 consecutive roots, then we can just say that the system is elliptic in nature. So, to define this problem, so we have just considered certain examples here. Consider a partial differential equation like del square u by del x square plus del square u by del y square, this equals to del square u by del z square here. So, if you will just take it into the left hand side here, we can just express this equation as del square u by del x square plus del square u by del y square minus del square u by del z square, this equals to 0 here. So, these coefficients are like 1, 1 and minus 1 here. So, if we will just take this coefficients in a matrix form here, then this matrix can be written as like uxx coefficient is 1, uyy coefficient is 1 and uzz coefficient is -1 here. So, if you will just go for these eigenvalues, then we can just write this one as like a minus lambda I, that is nothing but 1 minus lambda here, then 1 minus lambda here, -1 minus lambda here. So, the eigenvalues of A are all like 1, 1, -1. If all the entries in the diagonal are non-zero and the remaining elements are 0, then the diagonal entries are nothing but the eigenvalues. So, that is why these eigenvalues of A are all like 1, 1 and -1. So, if you will just see here, so two roots they have the same sign and one has the different sign. So, that is why this equation is hyperbolic in nature. So, second example, if you will just consider like a partial differential equation of the form del square u by del x square plus del square u by del y square plus del square u by del z square, this equals to 0 suppose, then we can just define the system as like the matrix as like a xx, a xy, a xz, then a yx, a yy, a yz, then a zx, a zy, a zz, and if you will just place this coefficients here, that can be written as 1 here, this is 1 here, this is 1 here, remaining elements are 0 here. And if you will just determine these eigenvalues, so that can be written as 1 minus lambda, 1 minus lambda and 1 minus lambda here, and the eigenvalues all are equals to 1 here. Hence, we can just say that this system is like or this partial differential equation represents a elliptic nature. Then we will just go for some standard forms of partial differential equations here. In a one space dimension, if you will just write this heat transfer equation, we can just write this one as del u by del t equals to k del square u by del x square here, where k is a constant. The above equation represents conduction of heat in x direction here, with u denoting the temperature at point x in a homogeneous medium at time t, and it also represents diffusion of like gas, fluid flow, etc. And if we want to express this parabolic equation in a two-dimensional form, then we can just express as del u by del t equals to k into del square u by del x square plus del square u by del y square. So, especially in the beginning of the lecture, whenever I was just speaking about this application, there itself I have just explained the second order partial differential terms in the form of like del square u by del x square plus del square u by del y square. This is called especially the diffusion terms here. And this del u by del t, this represents a time dependent variation of u there itself. So, that is sometimes called the transient problems, since it depends on time here. So, if you will just go for like a elliptic equation in a practical problem sense, then this elliptic equation describes the transient process, which can be expressed as del nabla square u equals to del square u by del x square plus del square u by del y square. This equals to f of x y here, where del square this nabla square, it can be represented as nabla dot nabla here. So, this nabla can be expressed as like I del by del x plus j del by del y here, and this operator nabla square is known as the Laplacian operator here. So, we can just say that this equation is a Laplace equation whenever f of x y equals to 0 here. When f of x y is a non-zero, then it is called to be the Poisson equation. So, especially we are just saying here that elliptic equations are known as potential problems, since these potential equations either it can be expressed as like Laplace equation or Poisson equation sense. So, then if you will just go for like a hyperbolic equation here, the most common hyperbolic equation in one space dimension is the wave equation here. If you will just see here, this wave equation is represented as del square u by del t square, this equals to c square del square u by del x square here. So, two coefficients involved here. So, that is why we can just express this one in the form of like b square minus 4ac here. And especially we have just defined this one, that if b square minus 4ac, if it is like greater than 1, this is a hyperbolic equation. So that is why if you will just see here that if you will just take this coefficient to the left hand side, we can just express this one as del square u by del t square minus c square del square u by del x square, this equals to 0. So the coefficient it will take as like a equals to 1 and c equals to minus 1 here. So that is why b square minus 4ac, if you will just take this one as a 0 minus of minus 1, this is nothing but 1 greater than 0. So that is why this is hyperbolic in nature, and this class of problems are appearing when this we will just consider the motion of a vibrating string stretched between 2 points, where u denotes the displacement of a point on the string at a distance x at any time t, while the string vibrates in ux plane here. In a 2 space dimension, it may represent deflection of a membrane sometimes. So if you will just go for this boundary conditions, like whenever we will just go for any solution of like ordinary differential equation or partial differential equation, it always requires some of these conditions to find the solutions. Either it is called your initial condition or it is called boundary conditions. So especially we can just say that the problem represented by a partial differential equation is said to be well posed if sufficient number of conditions are prescribed so that its solution can be determined uniquely. And if these conditions are prescribed either on the boundary or along the surface, it is called boundary conditions. Sometimes if it is prescribed, suppose at initial level, suppose at t equals to 0, suppose the conditions are given, this is called the initial value problems. So we can just say that when the conditions are prescribed on the boundary, these conditions are called boundary conditions. When prescribed on time, this is called initial conditions. So broadly speaking, both kinds of these conditions may be referred to as one of the boundary conditions, like the boundary conditions are Dirichlet condition, Newman conditions and mixed derivative conditions. Especially whenever we are just defining any real class of problems in partial sense, then one of these boundary condition is applicable in any real system. So for this Dirichlet condition, especially we can just consider that u is given directly or u can be prescribed at its value at all of these boundaries, that is specifically called Dirichlet condition. If the normal derivative is 0, then that is specifically called a Newman boundary condition. And if we can just consider this combining of both this Dirichlet condition and Newman condition, that is called a mixed condition here. This is just a combination of like a fixed value of u and normal derivative in multiplied with some like constant factors. Then we can just prescribe it on the boundary as alpha del u by del n plus beta u equals to gamma. Since our Dirichlet condition means we are just specifying the value u along the boundary, and Newman condition means we are just taking the normal derivative along the boundary, and if we are just combining both these two here, then we can just multiply one factor with this Dirichlet condition and one constant factor with Newman conditions, and both combinedly just forming this mixed condition here. Thank you for listening this lecture.